a ideia é que a gente encontrou, bom, até agora já começamos a estudar a energia livre em perturbation theory, então isso seria non-impacting free energy e primeira ordem, as correções de primeira ordem na potencial de reação. E usando o formalismo do Matsubara field integral, a gente viu que sempre se chega numa representação que tem aqui um somatório sobre frequências de Matsubara. Existe uma técnica como fazer esse somatório, é bem fundamental, essencial, porque isso sempre vai aparecer. E vamos discutir essa técnica, como fazer esses somatórios. A gente já, na verdade, deu os resultados aqui, mas ainda não foi mostrado como chegar lá. Então, isso é uma técnica bem importante que eu acho que agora vai ser a última parte assim, técnica, depois realmente vamos deixar esse problema e como realmente calcular free energy, e aí, bom, vamos realmente agora, depois disso, continuar com a física, mas essa parte técnica tem que ser feita. Bom, tá, então vamos começar. So I said, you have so far encountered, when you calculate the free energy, always this expression containing summations over Matsubara's frequency, so we need to know how to do these kind of Matsubara summations, Matsubara frequency summations. And this will, I don't know if it takes the entire lecture, but this will now take some time to explain the general idea, how one can efficiently do such summations over Matsubara's frequencies, and then we will study some examples. So this is the technical excursion then, topic of today's lecture, which is Matsubara frequency summation. And the question so that we want to answer is how compute sums of form so S like the sum, and here we have a sum over indices n, which label the Matsubara frequency, so this can be or bosonic or fermionic frequencies, and where H here is some function, and omega n is said is bosonic or fermionic. Okay, so this will be the topic, and let me first state the general idea how one can do such a summation here. So I will just write down the basic idea and then I'll get into detail. So I'll explain this a bit more, but the basic idea can be stated as follows. So when one has such a summation, it turns out that it is a good idea to introduce some auxiliary counting function. And as said, so I will explain this better. It becomes more obvious when one really looks precisely what it means. But first the idea. Let's introduce some auxiliary counting function, which we call g of z, which is a function in the complex plane and that has simple poles where the Matsubara frequencies are encountered. So this is, the entire idea is like using, results from complex integration. So this g is a complex function that lives on the complex plane, and it has exactly at this discrete values of the fermionic or bosonic Matsubara frequencies. This has simple poles, and then one has induced such a function. Then the sum, as written down there, can be interpreted as the sum over the residues of this function. So the residues of this function correspond to the Matsubara frequency, so we interpreted this as the sum over the residues which one obtains by integrating the product g of z times h of z along a suitable path in the complex plane, and this actually then gives us a lot of freedom to deform this path to then deform this sum into some integral which is more easy to calculate. Okay, so just, we'll put this, but the idea is, let's interpret this as a sum of residues of some helping auxiliary function g, so we can write this as integral over g times h over some properly chosen contour, and then we can deform the contour such that this gets simplified. Okay, that's like basic idea you should have in the mind, and now we try to be more precise to implement this idea. Okay? So first, we should introduce some counting functions g, which has the simple poles at the Matsubara frequencies. So there's actually two typical choices for this function g, which one encounters in literature. And I write down both of the choices. So one is given by beta is the inverse temperature, just the Fermi distribution in a way. Beta times z minus 1 for bosons. The Fermi distribution function for fermions. Okay, so this is one choice often encountered. So let's check. So recall that the Matsubara and frequencies, the bosonic and the fermionic, so the bosonic are just even numbers times P times temperature, and the fermionic are just the odd numbers times p times q, okay? This you should recall, okay? This is the bosonic Fermi distribution function. So if you look at this function here, one sees, yes, whenever this exponent is a multiple of, okay, I should so let's first write down here. So simple poles at z equals I omega n, and the residue is the plus or minus 1 for the bosons at Fermi. So this is just psi. So this is plus 1 bosons, minus 1 fermions. So if we look at this expression here, indeed for d equals I omega n being a multiple of 2 pi t, this here is just giving us a 1. So this has a pole here. And if you just, linearize this around this pole, you see that this has a simple pole with value 1. Okay? But the same way for the fermionic distribution, well, there we have another difference to this, a factor IPT here, which just switches the sign here. So again, this has a simple pole at now a fermion Matsubara frequency, but because of the minuses, the residue is then minus 1. Okay? So this would be the kind of counting functions mentioned here, which have simple poles at the Matsubara frequencies. So this is one choice that people use. Let me just write down another choice that you also find a lot of literature. And actually, it's not by chance that these are just the fermionic and the bosonic distribution functions. So that's, in a way, how the distribution functions will enter through the, if you use the Matsubara frequency techniques. So, second form of counting functions often encountered is just differs by this choice by a constant. So it's given by beta half cotangent for bosons, and it's tangent hyperbolicus beta z half. So that's another choice that you encounter in literature. Now this, again, these two functions have simple poles at the Matsubara frequencies. However, now both have just residue 1 in both cases. Okay, so this is one difference. Now there's another difference which sometimes singles you out. So if you can apply both of the functions, of course they should give the same result. Now in some cases, actually it is the convergence that you use. So you want to represent this sum here, some integral as a, where you integrate a product of this counting function times this function h, and there's some cases in which convergence of this integral that you write down forces you to use either one of the two. Okay, so we will see examples for this. And then another statement, maybe also, it's kind of funny because it's somehow a little bit separate, so you find probably this kind of choice more in the American literature, this here more in the Russian. Okay, that's a little bit cultural difference between what we use. Okay, so this is first of all two choices of counting functions, and I mean, if you like, you should verify yourself. Okay, you see the simple poles popping up at these Matsubara frequencies, you can convince you also about the value of the residue. Okay, so that was the first step. So we have introduced a function g. So now what we want to do, function g. So now what we want to do is we want to take the sum here and write this as an integral where you integrate the product of the two functions, okay? So let's do this here. let's consider then the following integral. We take 1 over 2 pi I. Take some integral in the complex plane along a contour which I call gamma 1, and I will draw in a minute. And then we integrate this product of functions. Okay? So G now is either choice of the counting functions. The H is the one that appeared in the sum. So this is the one where we want to do Matsubara summation. Let me just make here a plot in the complex plane. So here would be imaginary of D, here would be real of D. So at D equals I omega n, you have the poles. Let's take bosonic, which have a 0, 1, the I just shifted. And what you see now, if I take here the integral as 2 stripes or 2 paths going from minus imaginary infinite to positive infinite, and then I close in infinite and go back here. So if I take this closed integral, I will see that if I take this as a contour here, what this boils down to, well, I can just shrink this contour and I will pick up, provided this H doesn't have any poles in here, but you can always confirm that, I mean, in the cases you want to apply this as a case, then you can just see that you can deform this contour here into little circles where you pick up exactly the residue of this function here. So this is like counterclockwise, so you pick up a factor 2 pi I, and then depending on which function you use, like if you take this choice, then you should add here xi, depending if you have bosonic or fermionic, plus or minus. If you take this choice, there would be 1 in the case. But let me just write down here this xi for taking into account the residue. Okay? So this here, just to make clear what I said, boils down to deformation. If you deform this into this, and so on. Okay? So here the contributions just cancel from these 2 paths. Then this boils down to a sum. You pick up a 2 pi I, because you're counterclockwise. Then you take the residue of GZ, H minus ID, and this you have to evaluate now exactly at points where you have the simple poles, and this is Z equals I omega n. Okay? So if you plug in now the residue, this just gives you the value xi. Okay, so you get xi squared, 2 pi I over 2 pi I. You've evaluated this, and then you have to evaluate I minus ID at I omega n. This is H of omega n. So this is just 1 and this cancels, so this is exactly the sum that we were interested in. Okay, so this is just like the idea. We express the sum as some integral over some contour where we introduce this counting function. Okay, so introduce the function, we write the sum as sum over residues obtained by integration over the product G of Z, so this should be minus n, okay, along a suitable path. Now, the entire idea is, well, what we gain from this is that now we have the flexibility to deform this contour. So if we would take these circles, we are at the sum we started out from. But if we then start from this here, we can now deform this contour in a way to simplify this integral, namely in a way that now we can look at the complex structure of this function h. And in many cases, this function h, for example, just has simple poles somewhere in the complex plane. So then the idea is to, instead of doing this infinite sum here over the Matsubaras, we start out from this expression here, deform this contour, and just pick up the poles of this function h. Okay? So if this has simple poles, then we have reduced the sum over infinite Matsubaras just to its finite to some of finite number of poles. Sometimes this function h has a cut somewhere, and then we have to integrate along the cut. But oftenly, I mean, we can deform this contour gamma 1 into something that is much more easily done than the sum here. Okay, so that's the entire idea. Let me just maybe write down this once more here. So this was like the basic idea. Now we have put this into some formulas, and let me just now write down once more like the basic idea here, and then we have to look at some examples. So the idea is once you have start from here, you can deform the contour or integration path gamma 1. That is, you are free to deform contour in a way that the integral can be done. Okay, and the best is really to look at this, some examples. Okay, do you already know this technique, or is it new, or? Okay, it's. But is the idea clear, or yeah? So let's first consider one example. So let's consider the sum omega n minus t omega n squared plus some constant a0 squared, and omega n here are, let's say, the fermionic Matsubara frequencies. So this would be the sum we start out from. So let's first write this in the form given there. So okay, just one intermediate step. So let's write this here as I omega n plus a0 times I omega minus I omega n plus I omega. Okay, so this is just one intermediate step, just taking the product. Okay, so now we have started here. We can write this now in the form we said here. So let's choose one of the distribution functions. Let's take the Fermi distribution function and just use the idea where this gamma 1 now corresponds to this integration here. We we introduced the counting function, which here is the fermionic distribution function, and then we set d plus minus a0. Okay. So what I just used here is this expression given here. Okay. Okay, so the minus is from the residue. Okay, we said for the Fermi distribution function we have a residue minus, so there's a minus here, and then I just switched. Here's a signal. Okay, it's a minus, and the temperature was compensated by the theta. Okay, so let me just make a drawing. So this was just step that we set. We have here imaginary part of the, here real part of the. We have the fermionic Matsubaras, and everything we did is just write down this integral along some contour gamma 1. Okay. So now we can do exactly what we said before. So this function here has all the poles here, but this function here has just two simple poles, okay? One at a0 and one at minus a0. So let's call this a0, this is minus a0. Okay, so now what we can do is we can just take this contour here, instead of closing it at infinite this way, we can start to inflate it. Just take this part here and push it here to infinity, okay? So if we take this here, we will arrive something like this, so we can then close it here, then blow this up to infinity, and we will end up here with some path encircling this pole here in a clockwise direction, and the rest inflated here to infinity, and we have here some path again which just encircles this pole into infinity, and the rest also inflated to infinity. Now this integrand here falls off as 1 over z squared, so this...
A soma original nem é com menos ômega zero, né? A zero. A soma original é ômega 2 menos a zero ao quadrado.
Ômega... O que?
A soma original, o denominador.
Aqui. Ômega n quadrado mais a zero quadrado, né?
Não é menos?
Não, mais. Porque se eu faço aqui, é mais, né? Não, mas o ômega, eu fiz, olha, você tem que pensar, o ômega n são os Matsubaras que estão morando aqui no eixo puramente imaginário. Agora, essa troca que eu fiz pela contour integral, eu substituí o ômega n por iz, tá? Eu escrevi essa aqui, agora eu substituí o i ômega n por menos z, bom, eu troquei aqui o sinal e z aqui, tá? Tá? Por isso agora tá certo? Okay, so this integral here falls off quickly at infinity, so we can neglect, so there's still, apart from this two poles here, there's this infinite circle that we can just inflate to infinity. This doesn't contribute, okay? So if we do so, we just get, if we change this to now what we can call gamma 2, so gamma 2 would be these two poles. This is the change of contour that we did. And then what we do is we just pick up, in this part, we pick up the value of z equals minus a0. So this gives a 1 over minus 2a0, and then we get an exponential minus beta A0. This one contribution with, now we have to be careful, this is clockwise, so this we get with a minus 2 pi I. Minus 2 pi, this will cancel this one. Then we have a second contribution where we pick up the pole at A0. So this will give us a 1 over 2 A0 and an e to the beta A0 plus 1. Again, with a minus 2 pi I because it encircles this here again clockwise. Okay? So just write down the result. You can wipe this away, no? So this thing is, in both cases we have a 1 over 2 A0, so one has to be a little bit careful with the signs, but you see you get the both signs because one is at plus A0 and the other one minus A0. Okay. So if you like, you can rewrite this as minus tangent hyperbolicus beta A0R over 2A0. Okay, so this would be one example where we started out from an infinite summation, and by using this trick we saw that deformation of the contour really is very helpful because we only have to consider two poles. Okay? Now as an exercise, I would recommend you that you verify that you get actually the same result using the other counting function. So instead of the Fermi distribution function, the tangent hyperbolicus. Just a simple example, go through the same kind of argument using the other. Okay. Then you have to be a bit careful because the tangent hyperbolicus. Okay, so this was one example which actually, I guess we can generalize. Did I generalize this? I mean, let me just let me just generalize this example to obvious now. If you encounter some function h which has equal poles. By this generalization, what we have just studied, if the function h has isolated poles or singularities at some set of values in the complex plane which we know decay, and also the product of g, the counting function, and h decays sufficiently fast as z goes to infinity, then generalizing, like this is exactly an example that we studied that fall into this category. So we had two simple poles, plus minus A0, isolated in complex plane, and this integrand here falls off quickly at z going to infinity. Then one will usually try to inflate the original contour to an infinitely large circle. So that's what we did. Because the infinitely large circle won't contribute. Okay, so if you inflate it to an infinite large circle, the infinite large circle doesn't contribute due to this condition. But while inflating the circle, the starting contour to the infinite circle, you can pick up, or you will pick up exactly the poles of the function h. Okay? So the idea is that then gamma 2 does not contribute, and just formalizing what we have done in this example. So if you, again, psi is 0 or not, depending on the choice of distribution function that you start, that you use. So starting out from the sum, then this integral over the original contour, then what you arrive at is by I, then you have the sum over the dk, and what you integrate is over like little circles surrounding the point dk. That's what this contour means here. Okay. So this was the two contributions from the one pole here to one pole here. Okay, so here's the little circles, and then these intervals over the little circles of the poles just gives you the residues times 2 pi I. And again, always happens that if you start out from a contour counterclockwise, once you deform it to infinity, you will pick up the poles there by contours which are clockwise, so you typically will get a sign there, which is minus, because inflating makes you here little circles around the poles, which is clockwise. Okay, this is the clockwise nature, and then you get just the sum over dk, where you have to take the residue at dk. Okay, so can just make this once more in the drawing. Just generalizing of what we did in the example, you start out this imaginary V, real V. You have the poles here, the fermionic or bosonic, so here. So you start out from this contour gamma 1. Then you might have some isolated poles zk. Okay, so this would be like v1, v2, v3, v4, and so on, where this function h has its poles. So if we inflate this to infinity, we reduce this contour to just these little contours encircling this here, and an infinite circle gamma 2, which will just inflate it to infinity so it doesn't contribute, and we end up with this expression here, which is just from these residues. Okay? So that's one case that one often encounters. And now one can also already see the see like the one comment that I made is that sometimes the convergence will tell you, the convergence means, or the property that you want that the counting function times the original function that you started out from, that this quickly decays as z goes to infinity. So this is very important, I mean, to neglect all the contribution from this contour. So there you see that actually sometimes this tells you like which function you should use. Like if you take the fermionic case, you have the tangent hyperbolicus as one choice, or the Fermi distribution function. So the tangent hyperbolicus just has the limiting values of 1 and minus 1. Okay? But the Fermi distribution function in one case goes to 1, but in the other case goes to 0. Okay? So then you see that, well, sometimes you want to exactly use this property of the Fermi distribution function for z going to infinity, that this drops to 0 to kill you, like the integrand as z goes to infinity, positive infinity, and then you are just like worried with some part. Okay, so sometimes the Fermi distribution function will be better for the convergence or for this property, but this will be also seen in some examples that we look at. Okay, questions or? So this is like probably the simplest kind of integral that one can often reduce this Matsubara summations to. But then there is more complicated examples, and this is actually when this function h that we had here, if this doesn't have simple poles, but for example has cuts, okay? So it can also typically have cuts close to the real axis. So what you can then do is you can still deform the contour, but then instead of reducing the Matsubara summation to a sum of individual poles, you reduce this to then still integrals. And one example of this cut actually encountered in one of the examples. So the summations that I wrote down in the beginning were the two results that we had for the free energy. So one was the non-interacting free energy, which was log, so the sum of the log of I omega n, and then plus the spectrum. This log, of course, doesn't have simple poles, but has cuts. So let's then study as a second example, which is a little bit more evolved, the function where you actually have a cut at the real axis. Okay, so this is the second example. Should we do it now, or you want to have a break? Let's make it 5 minutes.